Hello, everyone. Right, so my name is Singh-Blom. I'm the machine learning craft lead at Embark Studios, and I'm going to be talking about machine learning implementation at Embark. So who is Embark? Who are we? We're an Nexen studio based in Stockholm, Sweden, and we have released 2 games so far. The first one is The Finals. There, The Finals. A free-to-play first-person shooter, tons of fun destruction, deep tactical game mode, and really amazing cosmetics that I'll talk a little bit later in this talk. The second game is Arc Raiders, a third-person PvP extraction adventure game. It's physicsy and grounded, and you battle these big Arc robots in a ruined future. And you have to watch out for the other raiders, the other players, because some are nice and help you, and some might be mean to you and take all your stuff. So be careful. So, the structure of this talk is in 4 parts. First, I'll talk a little bit about Embark machine learning in general, what we do and how we think about it. And then I'll have 3 different little examples of AI and machine learning at Embark. Personalized recommendations, where we bring something neat and easy to production. LLM quest analysis, where I talk about how to use language models for quests, but also how important arrows are. And robots, finally, in Arc Raiders, and how we got those to work. So let's start with machine learning at Embark. So Embark as a studio was founded with a few key philosophical ideas that we had. And one of them was, the key one was that it's too hard to create AAA video games. A lot of the founders came from DICE and Electronic Arts is a huge company, and we needed thousands of people to make these games that we're making, and it took years and years and years. And since there was so much money at stake and so much work at stake, it was very hard to take creative risks. So we took too few risks, and it was too hard to make them. So the founding idea of Embark is that we can, with new technology, we can make games faster, we can make them more fun, and we can take bigger risks and be bolder. So what do I mean by new technology? Well, I mean things like photogrammetry, where we, instead of making all the items and things in the world by hand, we go out and we take pictures of things, and using computers and tech, we stitch it together into digital assets in the video game. Or our character art pipeline, which is non-destructive and allows us to very quickly make new characters with new looks, and if we change our mind about something halfway through the production process, we can go back to an earlier stage and apply the change, and everything automatically follows and gets fixed by the pipeline, so we don't have to rework everything. Both of these things will be talked about in a later talk by Ivar and Michael, so go listen to that if you're interested in that stuff. But this is not machine learning. How does machine learning and AI fit into this? Well, AI and machine learning allow us to do 2 kinds of things. One, it allows us to do a lot of things faster. An example of this that has been very popular lately is these coding agents. We can ask Claude to help us write code, and it goes much faster. We can do similar things for art assets. We can make like delight textures, for instance. You take a picture of a texture that you want, it has a lot of shadows in it, we can use a machine learning model to remove those shadows. The photogrammetry things, there are things in the photogrammetry pipeline where we can use machine learning to make that go faster. These are things we used to do before, but faster. We make it more effectively. Then we can also use AI and machine learning to do new things. And here, I'm thinking about things like the robots that we have in Arc Raiders, the things we're doing with quests, personalization things that you just can't do if you don't have ML models to your disposal. And there's not really a strict difference between these 2 things. Sometimes doing things much faster allows you to do new things. So the boundary is not really clear, but there's still 2 different ways of thinking about how to use machine learning in video games creation. And we do both of them, Mark. But my team focuses mostly on the second box here, how to use AI and machine learning for new things that were not possible before. Here's my lovely team. And this is the best picture I got of the team. It's not everyone. We have a bunch of more people. But I just wanted to show you my dear friends and look at how beautiful they are. So let's jump into the first real topic of the talk, recommendations, where we bring something nice, neat, and easy to production. So I'm going to tell you 2 stories in this little talk. One neat recommendation trick and one neat organization trick. So first, let me give you the background. So the finals is a free-to-play game. So therefore, the store is very important. The only way we make money from the finals is that people buy things from the store, right? And we create a lot of content for the store. So over the years, we have, having had the finals for a bit more than 2 years now, I think. So it's more than 4,000 wearable cosmetics in the game, 2 years of catalog, and a very small store surface. And I realize in this setting, there are other people that have more than 2 years of backlog, but for us, it's still a big amount of assets and things that we're showing. So for us, it's a lot of things. And the fact that the store surface is so small makes it hard to expose all of these cosmetics to the players. So usually what we've been doing is we just have a new season, we have a few new cosmetics and battle passes that we show the players, and that's what they can buy, and they don't see all the old stuff that we made. So of course we'd like people to buy old stuff as well, because we've already made it. So we thought that this could be solved with a recommendation model. Sort of like Amazon does or Netflix does, like people who like this also like this. So we thought this should be easy. This is work led mostly by Junsi Kwang on my team. We thought this should be easy. We find a bunch of good models, we test them on our old data, train it on a few weeks of data, and see how well they do on the next few weeks of data. We take the winner of this and put it in real A/B tests and test it in production and see how well it actually does. We try these models: Bayesian pairwise ranking, Bayesian method, a deep learning-based method called multinomial variational autoencoders, and a few matrix factorization methods, including embarrassingly shallow autoencoders, EAS. So we tested this on this historical data set we had, and it was clear that for our setting, EAS was much better, both in terms of recall and mean reciprocal rank, which are two different measures that measure slightly different things. But the green bar is longest for EAS for both of these metrics, so it's clearly the best method. And it's an extremely simple model. It's literally 4 lines of Python code to train the model. So what you do is you take all the things that all the different items that we have, and all of the different users that we have for the game, players by items in a big matrix. You multiply it by itself, you add something on the diagonal, and then you invert it. And that's your prediction matrix. And then when you predict things, you just do matrix multiplication. So it's extremely simple model, this. 4 lines of Python code for training, 1 or 2 lines of code in effect for actually predicting things. Super simple. We found a place in the store to test this, the For You section of the store, which was the best, the sub part of the store most suited for testing. And normally that had shown just the most sold products in each category globally with no personalization. We added this personalization and we saw great results. 400% increase in number of buyers, strong increased currency spend with the in-game currency, and a significant increase in the US dollar spend for this section. And to be clear, this section doesn't drive the majority of sales. That's still battle passes and things like that. But for this section, we saw this great increase in spend. So huge success. Yet, we almost gave up on deploying this project. Why? Well, so first of all, it was hard just to know if people were interested. We tried, we talked to people, we didn't know who to talk to. And in a lot of organizations with machine learning research teams, the research team is sort of off to the side, right? And that was our problem. We didn't know who to talk to. We didn't manage to figure out if they were interested, like if we could get buy-in for the project. Very hard to get started on this. And after we had gotten some buy-in from the commercial team and people started being a little bit interested, we almost couldn't get the A/B tests approved. Why? Well, again, ownership troubles. We didn't know who was really responsible for this. The backend people said, oh no, this is too complicated, this is too much code to maintain these 4 lines of Python. We can't handle it, this is a risk, technical risks. People weren't sure about if we had the infrastructure to even do A/B tests. Lots of complications. And once we had the A/B test run and done, the initial live A/B test analysis showed no significant results. Why was that? Again, we were outside of the loop. The communications between our machine learning team that did the research and the data science team that did the analysis had different baselines. We analyzed different things. The communications broke down, and we had these reports in the beginning that said that this was not a significant improvement over baseline, even though we saw, when we did the analysis properly, we saw this 400% increase in number of buyers. So this was all really, really complicated, and we were really surprised at how hard it was to get this into place. And the solution, finally, for us, was nothing to do with the algorithm or anything like that. Of course, it was organizational. So what we did was we took the ML engineer, Junsik, placed him in the LiveOps team by literally just taking him off his chair in the ML office and putting him on a chair in the commercial office, in the LiveOps team. The communication overhead disappeared, testing, analysis, goals, all clear because he had daily communication and interaction with his colleagues that were not ML people. So here, we just moved him from outside to be inside, and all problems solved. So the thing we learned from this is it doesn't matter if your algorithm is simple and elegant if it's not deployed. And sometimes, often, something as simple as seating can unblock the work. So now that this has been unblocked, new algorithms and ideas can be tested each new season. It's easy to get new things into the game. So after the success with the initial ease model, we have now tried to improve that even more, and we do re-ranking on the candidates that ease gives us based on browsing history for the user. We put it together with the recommendations by the second best model that we had, the deep learning variational autoencoder, and the combination becomes even stronger. But these kind of things are only possible for us now because we have such easy communication with the actual LiveOps team that's running this whole thing. So it's easy to get things into testing, easy to communicate with the stakeholders there why this is important, and suddenly things go easily and smoothly. So that was my first story. Now let's jump to my second story, LLM question analysis, where I will talk about how arrows make people use tools. So I will tell you two stories, a cool application of large language models, and what really determines if tools get used. So, quests. Quests in Arc Raiders, and in a lot of other games, are fairly simple things. We have lots of quests in Arc Raiders. They're not super core to the loop, but they add something really fun to do for players in the game. And the quests have a lot of different properties. So we have the things like a quest giver. We have a quest name, a description of the quest, which objects are granted when you accept the quest, which rewards you get when you finish the quest, and the objectives that you need to accomplish in order to finish the quest. And, crucially, two more things. A quest gets unlocked by some conditions, frequently finishing some other quest, and a quest, when you finish it, in turn unlocks other quests. So the quests form some kind of graph. So this quest leads to this quest leads to this quest. So, and this is an interesting thing here is that some quests can unlock multiple other quests, and some quests need to be unlocked by a few other quests that unlock it. So the quests form a graph, and that's in contrast to normal narratives. If you read a book, or if you watch a movie, it's not a graph, it's just a line, a linear development of the story. So linear narratives, such as books and movies, the people who write the narrative are fairly sure of the order in which the people who consume the narrative will consume it. So you will start in the town, say, in the book. Then the adventurer goes off on an adventure. He meets the dragon. Then we go down one line, drinks the potion, go down one line, or go on to meet this horde of things that ChatGPT made for me. And then onwards, one step after the other. One page after page after page, chapter after chapter, scene after scene in a movie. We know what the order is. That's not true for video games. Video games and interactive narratives are messy. They're hard. So here, you might go on the quest first, or you might start with a side quest. You might continue to go down to the Meet the Dragon quest, or go sideways to the Meet the Dragon quest, or go downwards to the dog quest, or whatever. You can take things in different order. And depending on the order you did the quests in, your perception of the story will be different. You will remember having done different things than your friend who played it in a different order. And this makes it much harder to author, right? So frequently in video games, we get around this by like faking choice, right? You can do quest A or you can do quest B, but the result of both of these quests will take you to quest C, right? So we try to constrain the narrative space and make it smaller and make it easier for us who write the quests to follow. Right? And to properly QA these things, you need to read through all the permutations of all the various quests without getting bored and without like remembering things from last time you read through it that has changed and are different now. And I don't know any QA person who can read through these things over and over and over again without getting bored. Or do I? Well, we have someone who can do this, our friend ChatGPT. So LLMs are really good for this. They never get tired. They can read the story for the first time every time we call the API. So we can use them analytically instead of generatively. So we can make the LLMs read the quests and the order that we play the quests in, instead of write quests for us or write stories for us, something like that. So we let the LLM read the game. So if we simulate a playthrough that the LLM gets to play, we'll have something like first we go this way, then we go this way to the side quest, then randomly we do this quest, then this one, 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 then, oh, here the LLM got confused. Because the description of the forest quest or whatever talks about Bob the Merchant, but we already killed Bob the Merchant when we completed the quest The Merchant before. So now the LLM has found a contradiction, and it can highlight that and tell us, when we do it in this order, things get confusing. This doesn't make sense. Fix it. So a little bit, you can think of this sort of as unit tests or CI for narrative. Right? And we can do more with this. We can give the LLMs personas. We can say, you love PvP. Tell me when you get bored. You love lore. You're a lore nerd. Tell me when you want to have more information about the world or cool things and when you start to get bored. Or you are motivated only by loot. Tell me when you feel like the pace of the loot is not right and you think this part of the quest gets too little reward, this gets too much, right? So we can have different personas for the LLMs. So we tried this. We made a prototype. And the first prototype was fairly popular. So the way the narrative team works is that they have all the quest information, all the text, all the objectives, all of these things in Notion, which is the like wiki we use for this. We fetched the data from Notion. We built this web tool that could run simple analyses and do these LLM walkthroughs. And we found several inconsistencies and weirdnesses in this data. So it was really successful. We thought this was really cool. And then, when we were ramping up to actually launch the game, and the quests started to become more complex, we had more choices, more branchings in the quest chains, the narrative team stopped using the tool. Why? Well, it turns out all the data that we used for this, that we used to take from Notion, all the data about which quests are connected to which quests had moved to Miro, which is this whiteboard software. And the reason for that was that Notion is just text-based. And it didn't allow the narrative team to draw arrows between the quests and visually see which quests were connected to which quests. So Notion was better in all ways we thought about as a database and like containing all the information and having structured references to other quests and all these things. But for visually seeing how the quests were connected with each other, they needed a visual tool. And then all the fancy stuff with LLMs that we did was not as important for them as being able to take one quest node and draw an arrow to the next quest node. So it doesn't matter how fancy your LLM workflow is if the designers need to draw arrows. So ML tools, like all other tools, need to meet the users where they are. If the narrative designers want to draw arrows, we have to give them the ability to draw arrows. So we got a bit frustrated, I guess, and made a tool that we call Spindle that does the LLM stuff that I talked about, and critically, let's see it here, allows you to draw arrows. So we see like information on the sidebar, and there, click, boom. This was the functionality that we didn't have before that now unlocked this as a useful tool for the narrative team. And suddenly, they were back to using it, and they could also use it for this narrative support that we had before. So now they can jump in and select a few quests and say, run through this a few times and say where it gets confusing. And you see here on the bottom, this is the actual order that the LLM played the quest. And highlighted in the sidebar, it has some information about like, this I found confusing, this doesn't make sense to me, this lore bit that you mentioned here hasn't been explained properly, explain that better. So now they're back to using it, and we can integrate more and more things into it right now. So it's actually become kind of a fun one-stop shop for narrative things right now for our creators, where we can add things like progression info and rewards and all of these things as well, and have that as part of the single tool, and have a lot of LLM-based support for all of these things. Yeah. So now, finally, let me jump to my last part of the talk, robots in our creators. So first, let me show you the robots. Here. This one is called the Leaper, and you'll soon see why. He's made it angry now. And what a jump. And it fails with the landing and falls off. Jumps up again, and see the leg here? It hits the pole. Boom. A bit of an impact. And then it chases after the bear. There's a nice hero pose. And it gets him. Bam! And it impacted there a little bit as well. So there, we saw the big robot. And it does a bunch of interesting things. It falls off, it bumps into things, and it doesn't always look great, but the fact that it makes these little mistakes makes it look weirdly believable. So how did we end up here? So this is work done with a fairly large team here. Tom, Simona, Klaas, Ali, Peter, Hiki, Rezvane. Lots of people were involved in this work. So how did we end up here? Well, we knew when we started making our creators that we wanted a lot of replayability. And we wanted a lot of emergence in the game. So the emergence was the way we thought we had for getting replayability. New things happening every session. We also knew that we wanted big walking robots, because everyone knows big walking robots are cool. And we wanted grounding and physicality. And the key thing here is the physicality. That's the way that we thought we could get this grounding and the emergence, like one of the main tools we had for making each session be unique and new. Because when we simulate physics, things happen slightly differently every time, and you can't rely on like purely authored and scripted events over and over and over. So we wanted physicality and we wanted robots. How do we do that? Well, we knew people had done it before because we, like everyone else on the internet, had seen these videos. So if people can make physical videos, physical robots in reality, surely it would be possible to do that in a video game. And when we started Embark, we also had a bunch of inspiring papers coming out where they did really cool things with physics and machine learning in a sort of a game setting. So this is Deep Mimic by Xuebing Peng and others. It was a really nice paper that showed these physics-based robots that ran fairly fast and could perform fairly advanced motion patterns. So then the question is, can we too control our robots using physics and machine learning? And the answer is yes, by using something called reinforcement learning. So reinforcement learning is an old idea in machine learning. And it's fairly simple. I'll describe it to you. So in reinforcement learning, you have a loop between two different things. You have something called the policy, which is a neural network. And the policy sends out actions. It takes actions, which is some kind of numbers. And it sends those to the robot, to the agent in the world. And the agent takes these actions and does some kind of action in the world using them. So that goes into the simulation. And then things happen in the world because of these actions and because of the way the world is. And like it moves forward, it moves its arms, it falls over an edge, whatever. And then the robot observes what happens in the world and sends its observation back to the policy. And then based on the observations, the policy takes a new action. It goes back to the robot, it changes the state of the world and does something in the world, and gets a new observation, and it sends back to the policy. And then we have this loop of action, observation, action, observation. So how does it know which actions to take? Well, that's the second part here below. It's the rewards. So every time the robot gets some kind of observation of the world, we also measure some kind of reward during training of the neural network. So we measure some kind of reward that we as researchers have decided what it is. And based on the reward, we modify the policy to make sure that the actions it takes leads to as high rewards as possible. So we tweak the neural network so that the actions lead to high rewards. So that's reinforcement learning. And this worked fairly well for us. So we had some early demos with Unity things, with like game assets that we had taken over to like a Unity test project. And we saw what it looked like. And here the observations are the joint angles for each joint on the robot. It's the distance to the target player, and it's the angle to the target player. Those are the observations. The actions are the target angles for PD controllers in each joint. So we have like these motors, you can think of it as, and we tell the motors what angle they want to be at in order, and that's the action that the robot takes. And the reward that it's trying to maximize is the distance delta to the target. It wants to get as close as possible to the target player, and it wants to minimize the cosine angle between the body and the world up. So it tries to stand up. And it's also trying to, sorry, I'm missing one reward. It's also trying to minimize the angle between where it's pointing and the player. So it tries to look at the player. So we get these really nice organic movements. Notice here the butt drop. Let's watch it one more time. So at this sharp turn, the butt goes down slightly. That's not authored at all by us. It's just a result of the rewards and the physics. And I think it looks really nice and organic. We tried to put this in an early version of Arc Raiders. This is what we call the cylinder of pain. And here again, same kinds of observations, same kinds of actions, and the rewards here are also very similar. Like we try to get towards the target player, we try to keep upright, so we try to stand as upright as possible, and we try to face the goal and walk forward instead of walking sideways. And this was really fun. Like we noticed early on that it brought a lot of replayability. We got this emergence thing that we wanted as a design goal. But the gait, the way it walks, was not very nice. It's kind of floaty and wobbly and not exactly where we wanted it to be from an animation point of view. And then the question is, of course, how do we fix this? How do we make sure that this walks more stiffly and more robot-like, or whatever we want, like whatever our animation director says it should look like? And the way we did that was by tuning a lot of things. You can tune the stiffness of each joint, how strong the motors are, how damped the motors are, how we can change the proportion of the reward that should come from walking towards the player, and the proportion of the reward that should come from standing upright, and the proportion of the reward that comes from facing the player. We can add other rewards, like minimize the energy it uses, and then tweak the weight for how much that influences the total reward. So there's all these knobs that we can turn and tune here. So we spent years doing this, tuning knobs and parameters again and again and again, building lots of software to be able to keep track of our experiments and keep track of our results. And after years of tuning, we got something that looked fairly nice. So it rides itself, and it can walk in terrain, it has vision. And I think this gate is fairly nice. And here you see the physics. We can just throw it, and it does the right thing automatically. And now we will throw boxes at it and see it react. And these kind of reactions are really a key part of the reason why we wanted this technology, because this is the kind of, if players can interact with it in this way, it can be really fun. So that was cool, but we had a bunch of problems that remained here. And one of them is that it took a lot of time to get to this. Another is what we called behavior bleed, that this was one behavior that I showed you. It just walked towards the target. But if you want to have multiple behaviors, like walking towards the target and stopping, things get really complicated. So this robot here is trained both to walk towards the target with one set of rewards, and another set of rewards for staying still when we tell it to stop. So you see the little bar that switches here between stop and roam around. And how do I have a pointer? This bar here. Roam around and stop. And that works. It makes the robot stop. But we noticed very clearly that it makes it much worse at walking. So suddenly it became kind of scared, because at any time we might tell it to stop. So it's always a little bit paranoid that soon they will tell me to stop. I can't commit to walking fast like I used to, because sometimes they just tell me to stop, and then I need to be able to quickly stop moving, right? So it looked scared. So here, again, we have a problem here, that it doesn't matter how well a robot can traverse the terrain if the game designers can't easily control what they do and how they look when they do it. And the solution to this problem for us was a classical game AI solution that worked really well for us here, and that's behavior trees. So what we did in the end was that we trained one model, one robot, to always walk, never stop. It doesn't know what stopping is, full speed ahead all the time. And we trained another model to do the stop thing, walk, stop, that I just showed you. And then we have a behavior tree that the normal game AI designers control with normal behavior tree tools. And it's the one that says, now it should do the approach task, walk as fast as you can. And then we use the brain that we trained, the policy we trained, that never stops, doesn't know what stopping is. And it looks really good. And then when we should stop, we switch to the brain that has been trained with stopping, and we only ever show that brain the stop behavior. So even though it knows how to walk, but it walks carefully, we only ever use this brain with the stop flag on. So it always tries to stop immediately. And then we don't see this behavior bleed that I talked about before. Then the stop brain looks like a neat, pure stopping brain, and the approaching brain can move and look really nice when it's moving forward. And this also decoupled the brain engineering thing we did and like the machine learning reward shaping that we did from the combat designers and the designers' work on like making this work in the game. Now they could select that it should walk more often than it does, or all these things. And we didn't have to like do a new machine learning model every time they wanted to make a tweak. So now we could also add new behaviors much more easily, because they became sort of like Lego pieces that you can just add modules that you can add one after the other. And the abstraction of the behavior trees made them independent of each other. So now, after lots of tweaking, we had something that looked good, and we put this in the launch trailer for our creators, the first launch trailer before we rebooted the game, when the game was a different one that we ended up with. But we put this in the launch trailer. We thought this looks good. And we had this sort of similar setup as I've shown you a few times now. So we observe the joint angles, the distance to the target position, and the angle to the target position, and which behavior it's supposed to execute. We have actions that are the target angles for the PD controllers, and we have these super complicated rewards that involve the speed that it's traveling at towards the target position. It involves the cosine angle between the body up and the world up, the energy use, the torque use, impacts on non-foot parts. It involved facing direction. Like we had probably 10 or 15 different reward models that we had tuned so it had the perfect balance between each other in order to look good. And the problem with this was that this does not scale. Right? So if we wanted a new robot, we had to like redo all of this from scratch. If the animators came in and said, I think it should look snappier, or jumpier or heavier or oomfier or whatever words animators use, we had to retune all of these, and it would take weeks and weeks and months to change how it looks. So like we had a very, very big velocity problem here, like in terms of not being able to iterate quickly. So what we did, the problem here was how to make this thing walk like more like this or more like this. And how do we do that for lots of different robots at the same time, not just one single robot that we optimized for very, very carefully. And furthermore, we wanted more kinds of things than just movement, as I said. We wanted stop. We also wanted things like this, like hero moves, like stomping. What's the best reward function? Like, it's easy when you just say, OK, we reward it for going towards the target. That's easy. But how do you design rewards for making it stomp with its feet? That's super complicated. It's not at all obvious how to do that. And that's for like 1 foot. What if the designers now say, actually, could you make it with 2 feet instead? Then we have to redo it from scratch, and it might not give the same results. But luckily, as we were hitting this problem, and it became more and more of a problem for us, a really nice paper, this is again from Sjöbing and allies, a really nice paper came out called Adversarial Motion Priors that figured out how to use animations from an animator combined with this reinforcement learning setup. So we try this instead. So we go to our animator. He's also named Martin, just like me, at Embark. So we go to him and say, hey, give us a walk cycle for the robot that we're working on. Using the normal tools that animators always use, like they draw these curves and whatever animators do, right? And then we build this neural network that takes either a few frames from the animation that Martin made, or a few frames from the robot that we have in the game. And it learns to tell the difference. So the neural network learns to classify this either as made by Martin or not made by Martin. Right? And then, in addition to the rewards that I already talked about, we use this as a reward. So we say the robot gets more and more rewarded for looking like the stuff Martin makes. So that becomes one of the rewards. So now it has like an art reference that it's trying to imitate all the time. And this gives nice results. So now the artists are back in the loop, right? And if he changes his mind of how the robot should walk, he can just make a new animation. And then we can retrain it, and it's much easier to control. So here to the left is the robot using AMP, and it's frozen, and I don't know why. Anyways, you have to take my word. You saw the video in the beginning of this part. It walks nicely now. And this one here to the right is what it looked like before we had this reference animation. So it's much easier to make it walk nicely and look cool now than it was before. So animators know how things should move. Give them the tools to control the movement. Again, back to controls for the creatives in the game. Like, we need to make the tools be useful for the people that are doing the work. So now we have something that looks really cool. Here is from the server slam test we had in the beginning in March of last year. And it walks nicely. And people seem to like it. Shoot it! Oh my God! So that's nice. However, a few seconds later, we saw a problem in this thing. So this is the same scene now, the same players, same guys. One of them has been killed by the robot, and he's trying to crawl into this tunnel and escape. And we see this.
Right here.
Oh, man.
Pull me up. Don't do it. Don't jump. Okay, can you res me from right there? Oh my God, he's inside.
Wait.
Bro, dude, he's like physics-based. When he like jumps in, he like ragdolls.
And did you see the problem? The problem was that the robot jumps into the tunnel and then falls out, even though it should fit in the tunnel, right? We see that the robot is inside of the tunnel. Why doesn't it just go inside and kill the players, right? And the problem here is the vision system that we had built. So the vision system we had built, we had used for years at this point. And we've been sort of OK with it. The idea is very simple. Above the robot, in the air, we make this grid of points. And then from each point in this grid, we send a ray down and see where we hit the ground. So then we get a height map. You see these faint pink and yellow dots on the ground here? We get this height map around the robot that tells us how the ground looks like. And that's easy for machine learning, because machine learning and computer vision has built this thing called a convolutional neural network that's very, very good at working on grids. So we have the machine learning tools to deal with this very easily. It was also very easy to implement. We just make a grid above the robot, shoot it down, and then we see how high the ground is. The problems are also clear and obvious when you think about it. It doesn't work with overhang. If it tries to go below a bridge or inside of a tunnel, where should we shoot the rays from? Right? We don't know. It also gives it this weird way of seeing through walls. If it goes close to a wall, some of the grid will be on the other side of the wall, and it will see what the ground looks like where it can't see, right? So it's kind of cheating. So the solution for us was something called point clouds, where instead of shooting from a grid above, we shoot rays from the robot. And the clever thing with point clouds is that we can, since the points don't move in the world after, we can just record where the hits were and then reproject them to the robot's local coordinate system every frame. So we can just send a few rays every frame, which is cheap, and then reuse them and cache them for a second or so. So it's fairly computationally easy. The problem is that the machine learning methods for point clouds are much worse than the ones for convolutional neural networks, for grids. So we had less computing machinery to use than we had for the grids. But we did manage to solve it. It was harder to implement, but these point nets worked out in the end. And now we don't have problems in tunnels anymore. So now this is the same tunnel as I showed in the previous video, but 6 or 8 months later, just before launch, during what we call the server slam test, when we had the weekend before we launched Dark Raiders. So let's see the same tunnel, the same robot, different players, different time.
It looks sick though. Oh my god, it's rolling! Oh my god! Oh shit! Oh my god! Fucking run!
I'm too fat, man.
And there.
I'm dropping my shit!
Don't worry, they all die in the end. So, what did we learn from this? Well, I think the key learnings that I've tried to present in this talk are that algorithms and models are important. It matters what kind of algorithms you use. But organization is also important. A good model is only useful if people know about it and can use it. And often half of the work of getting machine learning to production is tooling and figuring out how artists and designers actually work and how we can fit into their pipelines. And that was what blocked us, both for the recommendation system, for the quest system, and frequently for the robot work here that I presented in the end. So if you want to do ML, by all means, spend time on the models, but also think about how the people that you work with will use the tools that you build. So thank you.